everybody, welcome back to Leetcode Simplified. I'm Alan, and in this video we're going to solve Leetcode 222. Count complete tree node. Given the root of a complete binary tree, count the number of the nodes in the tree. According to Wikipedia, a complete binary tree means every level is completely filled except the last level, which can be filled from left to right. Design an algorithm that runs faster than big O of n time complexity. Big one. This is not an easy problem despite what Leetcode says. We need to fully understand the properties of complete binary tree and perfect binary tree to come up with an algorithm faster than big O of n time. Let's start with the easy, straightforward recursive solution which runs in big O of n time. If the root is none, return 0 count. Otherwise, count the root itself as 1, plus the node count in the left subtree, plus the node counts in the right subtree. Done. Easy solution. Let's submit this easy peasy, not so crazy solution. Boom! Accepted. This works, but it's big O of n time complexity, too slow for large trees. The problem wants an algorithm that runs faster than big O of n time complexity. Let's improve with a much faster solution using the fact that a complete binary tree can also be a perfect binary tree. First of all, we need a helper function to compute the height of a complete binary tree. Initiate the height as 0. Because complete binary tree is filled from left to right, we can compute its height by going all the way left until the node is none. Increase the height along the way. H will be the height of the tree. So what is the height of this tree? 1, 2, 3. What is the height of this tree? 1, 2. What is the height of this tree? 1, 2. So again, the height of a complete binary tree can be computed by counting the nodes along the leftmost path, since the tree is always filled from left to right. Now back to our main function's logic. If root is none, return 0 count. Compute the height of the left and right subtree. Here is the crucial deduction we need to understand. If left subtree height equals right subtree height, that means left subtree must be a perfect binary tree. Return 1 count for the root plus the number of nodes of that left perfect binary tree plus the count of nodes on the right subtree. If the left subtree height is larger than the right subtree height, that means the right subtree must be a perfect binary tree. For example, if the blue right subtree don't have this node, then the blue right subtree is perfect. Return 1 for the root count plus the number of nodes of the blue right perfect binary tree plus the count on the red left subtree. Again, let me emphasize this very crucial deduction. Look at the yellow tree. If the red left subtree height equals the blue right subtree height, then the red left subtree must be a perfect binary tree. Otherwise, the blue right subtree must be a perfect binary tree. Why? Because a complete binary tree is always filled from left to right. So the left subtree gets completely filled first before the right subtree even starts. Oops, I see a small indentation error. Let's correct it. Okay, that looks great now. And we're done. But it's not easy at all. Alright, it's time to submit our code. Here's come the moment of truth. Boom, accepted, great. So computing the height takes big O of log n. And we do this up to log n times. So the total is log n times log n, much faster than big O of n. That's it. We solved Leetcode 222, count completely 3 nodes using an easy recursion depth first serve, big O of n solution, and a not so easy solution but optimized big O log n times log n using a complete binary tree and perfect binary tree properties. If you found this explanation helpful, don't forget to subscribe and check out my other Leetcode playlist, explained simply and clearly. I'm Alan and this was Leetcode Simplified. Thanks for watching and I'll see you in the next video.